Today we're going to be looking at lipids. Lipids are large biological molecules. Like carbohydrates, they're composed of carbon, hydrogen, and oxygen. Most lipids are nonpolar and hydrophobic because they have large, long hydrocarbon chains. If we take a look at hydrophobic as in terms of the word, hydro meaning water, phobic meaning fear. So if we took this literally, this would be a fear of water. Basically what this means is they're not soluble in water. Now, lipids can be saturated or unsaturated. If they are saturated, it means they have single bonds between all the carbon atoms. If they're unsaturated, they actually have double or triple bonds between these carbon atoms. And we'll look a little bit more about what that actually means as we go through this. So lipids are actually one class of biological molecules that actually don't form polymers. The lipids that we're going to look at today are fats, phospholipids, and steroids. So in terms of what function lipids have in our body, they are a high energy compact form of fuel storage. Lipids also provide insulation against heat loss for us. They provide cushioning for certain organs like the kidneys. They also regulate our metabolic processes. So how fast do we burn energy through steroids? And another important function of lipids is that they're a building component of the cell membrane. So phospholipids basically are a significant piece of the cell membrane. And we'll look at all of these as we go through. So if we look at fats first, a fat is constructed of two types of smaller molecules, a glycerol molecule and 3 fatty acid molecules. So when we put these 3 fatty acids together with the glycerol, what we call that is actually a triglyceride. So this is basically what a triglyceride looks like. This on the bottom is a triglyceride. So if we look at this, the glycerol molecule is the piece that we see in gray at the very top. That's a glycerol molecule. The piece that's in yellow at the top is a fatty acid molecule. So what happens is a dehydration reaction, just like when we looked at carbohydrates where we took monosaccharides forming disaccharides or polysaccharides, and we had dehydration reactions where we remove water and then we can link together the molecules. Same kind of idea here. These are different molecules that we're linking together. But what we're doing is we're actually removing a hydroxide, which is hydrogen and oxygen from the fatty acid, hydrogen from the glycerol molecule. So we're taking out 2 hydrogens and an oxygen. We're removing water. And when we do, then the carbon that's left can now link up with the oxygen, which is basically what's happening in this bond right here. So it does that a total of 3 times. We take 3 fatty acids and we connect them to that one glycerol molecule to give us a triglyceride. So basically what happens is we take the glycerol and in a step-by-step process, we take oxygen and hydroxide, we remove a water molecule, and then we produce one fatty acid that's now linked to the glycerol. We repeat the same process with the second molecule. Take out the water, so this piece right here, and we get a second fatty acid connected to the glycerol. And then we repeat that one more time, and we get a third fatty acid. So we now have triglyceride, and we've removed a total of 3 water molecules. So if we look at what type of reaction actually forms a triglyceride, this is going to be dehydration reaction. Now we wanted to talk about saturated versus unsaturated fats. So if we have a saturated fat, basically it's able to stack. It's in a basically a straight line, so they can layer each other quite closely together. The reason why they can get, or when they get so close together, then they are in solid form. So things like margarine, butter, lard that are in solid form at room temperature, these are saturated fatty acids because the molecules can stack close together. If I have an unsaturated fat, basically what happens is where a double bond happens, it causes the molecule to bend. So this molecule now is bent, and when it's bent, it's no longer able to stack as neatly as it can as a fatty acid. And because of that, it can't get close enough together to form a solid. So unsaturated fats are liquids at room temperature. So if we actually broke that molecule down, the picture on the right is a saturated fat molecule. And what you see is a single line between each carbon to carbon atom. Those are depicting a single bond. If I have a double bond between the carbon atoms, that forces the molecule to bend. And that's when we have an unsaturated fat. Now, something else that you'll see in grocery stores, if you've ever looked at labeling, is sometimes they'll talk about something being hydrogenated. If I have hydrogenation, basically what they do is they take and they add hydrogen to the existing unsaturated compound to make it saturated. So now it's going to be a solid at room temperature. These are some examples: margarines, shortenings. Basically, the advantage to doing this is when they're stacked together, they are much more difficult for our bodies to break down, which is one of the reasons we don't want saturated fats in our diet. But on the plus side to that, because they're more difficult to react, they have a longer shelf life. So if I can hydrogenate something as a manufacturer for certain food products, it increases the shelf life that I can put that product on the shelf. So from a financial perspective, if I hydrogenate a substance, then I can sell it for a longer period of time. Second group that we're going to look at in terms of lipids are phospholipids. So with a phospholipid, basically what we have is a phosphate group as part of the molecule, a glycerol molecule, which is also part of that, and then two fatty acid chains. So we've already looked at what glycerol looks like and what fatty acids look like. We're also going to see how the phosphate all comes into play with that. Now, the phosphate part of the molecule is actually polar. And because it's polar, it actually has a charge. And when it has a charge, it's actually hydrophilic. And if we look at these two, hydro being water, philic being loving, this is something that likes water. So it's actually attracted to water itself. The fatty acid piece is hydrophobic. In other words, it doesn't like water. So when we combine these two together, we basically have part that likes water and part that doesn't like water or repels water. So this is what a phospholipid looks like, this large molecule down here. So you can see the hydrophobic tails, or the fatty acids. We have two of them. This is the one part of the tail. This is the second part. So this is the pieces, if we looked at it from a different perspective, that's one half of the molecule, the bottom half. Then we actually have a glycerol piece in here and a phosphate piece in here. This phosphate, and why it is a phosphate, is it actually has phosphorus as part of this molecule. So that part of the molecule is hydrophilic. In other words, half of this molecule likes water, another half doesn't. If you think about this in terms of the cell membrane, so all of our cells have a cell membrane, and if we could magnify it so we could look at it, basically this is what the cell membrane looks like. It's two layers of phospholipids that are end to end, or I guess tail to tail rather. So the part that doesn't like water is on the inner portion of the membrane. The part that likes water is on the outer portion of the membrane, which of course is important because our bodies are composed up of mostly water, and therefore so are the cells. Steroids is another type of lipid that's also important in our body. Some types of steroids are actually hormones. So for instance, estrogen and testosterone are types of hormones that are steroids. Another type of steroid is cholesterol. So basically as a building block, cholesterol is kind of the building block that forms the basis. Cholesterol is a 4-carbon ring, which these are in yellow, but those are the part of the 4-carbon ring of a steroid molecule. So basically I can use this to build other steroids. Now cholesterol is actually only found in animals. Not only is cholesterol important because I can create other types of steroids or hormones from them, cholesterol is also important because it's actually a component of the cell membrane. So phospholipids form most of the cell membrane, but there's also cholesterol embedded within that, and that helps to keep the membrane fluid. Now, we talk about cholesterol in our bodies, and people worry about cholesterol, but what exactly does it mean? Well, we have substances in our bodies called lipoproteins. These lipoproteins are used to actually carry fats around in the blood, but for different purposes and to different places. So things that are typically insoluble, like our triglyceride, or phospholipids, or cholesterol, those have to be transported because they're not soluble in water. So that's the function of the lipoproteins. Basically, a lipoprotein has a lipid piece and protein piece. We have different types of lipoproteins. So LDLs, or low density lipoproteins, will actually deliver the triglycerides and cholesterol from liver into the tissues in our body. When that happens, it can increase our risk of plaque because the transport, sometimes it can end up being on plaque on the blood vessels as it moves through the body. The HDLs, or high density lipoproteins, are actually beneficial for our body. Well, not that LDLs aren't either, but there is the issue of potentially having plaque because they're moving from the liver to the tissues of the body. So HDLs do the exact opposite. Basically what they do is they take it from the body and return it to the liver. So they scavenge extra cholesterol and phospholipid, take them to the liver. So if I have a high level of LDL cholesterol, it's indicative of increased risk for heart attack. Whereas if I have a high level of HDL cholesterol, it actually lowers my risk of heart attack. So if we're looking at our cholesterol level, you want to have a cholesterol level of less than 200 milligrams per deciliter. When you look at the cholesterol value, this is the total cholesterol, including LDL, HDL, and other lipid components. The other thing that they'll often assess when they're looking at your cholesterol is your triglycerides, because that's a piece of the overall cholesterol. You want that value to be less than 150 milligrams per deciliter. The good cholesterol, which is HDL, you want to have that greater than 35. And the bad cholesterol, or the LDL, you want it to be less than 100. So if you look at your cholesterol level compared to your LDL ratio, if it's less than 4.5, it's indicative of heart disease. So it's one of the ways that doctors can test your blood and analyze your risk for heart problems. So we'll stop there for today.